Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to talk on module Multipole Fields Part 2 under the paper Electromagnetic Theory. So students, let us see what we are going to learn in this module. First, we'll see the properties of multipole radiations. Then, energy contained in electric and magnetic multipole radiations. The angular momentum of the electric and magnetic multipole radiations, and lastly the detailed angular distribution of the electric and magnetic multipole radiations. So now what is electric and magnetic multipole fields? In the last unit, we had started with the general discussions of the multipole fields. We had obtained the spherical wave solution of the scalar wave equations in terms of the spherical Bessel functions. We had then introduced the spherical harmonics and the operator L, which is equals to minus iota into r vector cross del, which is familiar to the students from quantum mechanics. Next, we described some properties of this material operator. Further, we took up the task of finding the spherical wave solution of Maxwell's equations. These being vector equations, their solutions were also obtained in terms of the vector spherical harmonics, that is L vector into YLM. We have two types of solutions, electric multipole and magnetic multipole solutions, that is ELM R theta phi is equals to Z naught GL dependent on KR, L vector YLM dependent on theta phi, and HLM M is equals to minus iota 1 divided by Z naught K into del cross E vector LM M, and HLME vector dependent on r theta phi is equals to F1 dependent on KR into L vector into YLM dependent on theta phi, and E vector LME is equals to I naught Z naught by K into del cross H vector LME, where Z naught is equals to under root of mu naught by epsilon naught. The normalized spherical harmonics are x vector Lm as a function of theta phi is equals to 1 divided by under root of L into L plus 1 into L vector into y Lm as a function of theta phi, where L is not equals to 0. And the general solution of Maxwell's equations are H vector equals to summation Lm of AE as a function of Lm into F1 as a function of Kr into X vector Lm minus iota by K Am as a function of Lm into del cross GL as a function of KL into XLM vector. E vector is equals to Z naught into summation Lm of Am as a function of Lm into GL as a function of Kr into X vector Lm plus iota by K Ae as function of Lm into del cross Fl as function of Kr into X vector Lm, and Am Lm into GLKR is equals to K divided by under root of L into L plus 1 into integral of YLM star as function of R vector and H vector d omega, and AE Lm into F1 Kr is equals to minus K divided by Z naught into under root of L into L plus 1 into integral of YLM star as function of R vector and E vector into d omega. We now continue with the study of multipole fields. Our next task is to find the properties of these multipole fields, that is energy and angular momentum. So, let us look at the individual multipole field. Fl as a function of Kr is a linear combination of two spherical Bessel functions NL and JL. In the near zone where Kr is far less than 1, we have JL tending to 0 and NL as a function of x tends to minus in 2L minus 1 factorial divided by x raised to power L plus 1. This implies that H vector LME tends to minus k divided by L into L vector into YLM divided by R raised to power L plus 1, and E vector LME tends to minus iota Z0 by L into del cross L vector YLM divided by R L plus 1. Iota into del cross L vector into YLM divided by R raised to power L plus 1 is equals to del cross R cross del into YLM divided by R raised to power L plus 1 is equals to bracket R vector into del square minus del vector into 1 plus R into del by del R bracket close whole into YLM divided by R raised to power L plus 1, which is equals to minus del into 1 plus R into del by del R whole into YLM divided by R raised to power L plus 1, which implies that E vector LME tends to minus Z0 into del of YLM divided by R raised to power L plus 1. The presence of gradient gives one higher power of R in the denominator, so that in the near zone the electric field dominates over the magnetic field. The magnetic multipole fields can be obtained in exactly the same manner or by simply noting that the roles of E vector and H vector are interchanged according to the transformation. For magnetic multipole, E vector E tends to minus Z0 B vector M and B vector E tends to E vector M divided by Z0. In the far zone, Kr where is far greater than 1, Fl dependent on Kr could be approximated to HL1 Kr, which tends to minus iota raised to power L plus 1 into E raised to power IKR divided by Kr. So this implies that H vector LME tends to minus iota raised to power L plus 1 into E raised to power IKR divided by Kr into L vector into YLM. Keeping only the highest power of R in the far zone, we have del of E raised to power IKR by R is equals to IK into E raised to power IKR by R, and E vector LME is equals to minus into minus iota raised to power L plus 1 into Z0 E raised to power IKR divided by KR into bracket start N vector cross L vector YLM minus 1 divided by K whole into R del square minus del into YLM bracket close. So this implies that E vector LME is equals to Z0 H LM E vector cross N cap. These fields are typical radiation fields, falling off as 1 divided by r. For the magnetic multipoles, E vector m tends to z naught, B vector E, and B vector m tends to minus E vector E divided by z naught. So energy in the multipole radiation. So in 4, replace Fl as a function of Kr by HL1 Kr. Vector HL is equals to summation m AE as a function of Lm into XLm into HL1 as a function of Kr into e raised to power minus iota omega t, and EL vector is equals to I naught Z naught by K into del cross HL vector. Time average of U is equals to 1 divided by 4 epsilon naught into E vector dot E vector conjugate plus Z naught square into H vector dot H vector conjugate equals to half epsilon naught Z naught square into H vector dot H vector conjugate equals to 1 divided by 2 mu naught H vector dot H vector conjugate. Now replace HL1Kr by its asymptotic form, that is HL1x tends to minus iota raised to power L plus 1 into e raised to power ix divided by x. Then energy in spherical shell between r and r plus dr is du is equals to mu naught dr by 2k square into summation m dash of ae conjugate as a function of L m dash and ae as a function of Lm into integral x Lm dash conjugate into x Lm d omega. This implies that du by dr is equals to mu naught divided by 2k square summation m of mod ae as a function of Lm square. For a general superposition of electric and magnetic monopoles of all L values, there will be summation over L as well, and corresponding magnetic multipoles will also be added, and we get du by dr equals to mu naught by 2k square into summation Lm of mod of ae Lm square plus mod of am Lm square. So the total energy in a spherical shell in the radiation zone is an incoherent sum over all multipoles. Now let us see what is angular momentum of the multipole radiation. Let us now find the angular momentum carried by the radiation. The density of the angular momentum of the field is, that is, we use the symbol small m for density of angular momentum of field and capital M vector for the total angular momentum to avoid the confusion with the angular momentum operator, that is capital L vector. So now let us study about the angular momentum of the multipole radiations. M vector equals to r vector cross p vector field is equals to epsilon naught r vector cross e vector cross b vector equals to epsilon naught mu naught into r vector cross e vector cross h vector equals to 1 divided by c square into r vector cross e vector cross h vector. This implies for harmonic fields, time average of m vector is equals to 1 divided by 2c square into real part of r vector cross e vector cross h vector conjugate, and on using e vector equals to iota z naught divided by k into del cross h vector, and time average of m vector is equals to mu naught divided by 2 omega into real part of H vector conjugate into L vector dot H vector. The total angular momentum in the shell between R and R plus dr in the far zone region is now dm vector equals to dr mu naught divided by 2 omega k square into real part of summation m dash of ae conjugate as function of l m dash into ae as a function of lm into integral L vector dot x vector Lm dash whole conjugate into x vector Lm d omega. On using the explicit form for x vector Lm, we have dm vector by dr equals to mu naught divided by 2 omega k square into real part of summation m dash of a e conjugate as function of lm dash into ae as function of ln into integral y lm dash conjugate into L vector into y lm d omega. On using properties of spherical harmonics and n vector into ylm, we have dmx by dr equals to mu naught by 4 omega k square into real part of summation m of under root of L minus m into L plus m plus 1 into ae conjugate as a function of L and m plus 1 plus under root of L plus m into L minus m plus 1 into ae conjugate as function of L and m minus 1 whole into ae as function of lm. Similarly, dmy by dr equals to mu naught divided by 4 omega k square into imaginary part of summation m over into integral L minus m into L plus m plus 1 into ae conjugate of L and m plus 1 minus under root of L plus m into L minus m plus 1 into ae conjugate as function of L into m minus 1 whole into ae as function of lm. And dmz by dr equals to mu naught divided by 2 omega k square into real part of summation m into m and mod of ae lm square. The expression for z component is simpler than for the x and y components because of the way the spherical polar coordinates are defined. For multipole with a single m value, we have mx equals to my equals to 0 and dmz by dr equals to m by omega into du by dr. This is a relation between energy and angular momentum in classical physics. In quantum mechanics, these equations have a familiar interpretation. The radiation from multipole of order L, m carries off m into h cross units of z component of angular momentum per photon of energy, that is h cross omega. Even with the superposition of radiation with different m, the same interpretation holds. Now each multipole of definite m contributes incoherently to the z component of angular momentum. In this case, however, the x and y components of angular momentum are also non-vanishing, with multipole of adjacent m components contributing to the sum. All this is of course familiar in quantum mechanics. Similar results hold for magnetic multipole radiation as well. For superposition of both electric and magnetic multipoles, we have dm vector is equals to dr mu naught divided by 2 omega k square into real part of summation m dash bracket start ae conjugate l dash m dash ae l m plus am conjugate l dash m dash into am l m bracket close into integral of L vector into x vector L dash m dash whole conjugate into x vector L m d omega plus ae conjugate L dash m dash into am L m minus am conjugate L dash m dash into ae L m bracket close into integral L vector into x vector L dash m dash conjugate into n cap cross x vector L m d omega. The interference term comes from terms whose electric and magnetic multipole differs by unity. In quantum mechanics, mq square divided by u square is equals to mx square plus m by square plus mz square whole divided by u square is equals to L into L plus 1 divided by omega square. While classically, as we have seen, mc square divided by u square is equals to mz square divided by u square equals to m square by omega square. The reason for this anomaly lies in quantum nature of the electromagnetic field and the uncertainty principle. According to the uncertainty principle, if the z component of angular momentum is known precisely, the other components will completely uncertain because the three components of angular momentum do not contribute each other. However, their mean square value is such that equation holds here. All this is true in quantum mechanics for a single photon state. If, however, the radiation contains many photons, the classical limits, the mean square value of the transverse components can be made negligible compared to the z component. It can be shown that for a state containing n photons, mqn whole square divided by un whole square is equals to n square m square plus n L into L plus 1 minus m square whole divided by n square omega square. Now let us see the selection rules and parity. Between two states J and M and J dash M dash, possible multipole transitions have Lm such that mod of J minus J dash less than equals to L less than equals to J plus J dash and M equals to M minus M dash. Now here parity is conserved in electromagnetic transitions, and if the initial and final states have same or opposite parity, transitions between them takes place through multipoles of even or odd parity respectively. The parity of a multipole field is determined by that of its magnetic field. So for electric multipoles, H vector L is equals to summation M over AE as function of Lm into X Lm vector into HL1 as function of Kr equals to e raised to power minus iota omega t. And parity transformations are r vector tends to minus r vector, which is equals to r tends to r, theta tends to pi minus theta, phi tends to phi plus pi, which implies that YLM tends to minus 1 raised to power L into YLM, and L vector is equals to r vector cross p vector tends to L vector, which implies that L vector Le tends to minus 1 raised to power L into H vector Le. Parity of electric multipoles is minus 1 raised to power L. Similarly, parity of magnetic multipoles is minus 1 raised to power L plus 1. If the parities of the two states are same, only odd or magnetic dipoles and even or electric dipole transitions are allowed. If the two parities are opposite, the allowed transitions are odd or electric multipole and even or magnetic multipole. So now let us see the angular distribution of the multipole radiation. The fields given by equation in the radiation zone reduces to vector B tends to e raised to power I into kr minus omega t divided by kr into summation Lm of minus iota raised to power L plus 1 into Ae as function of Lm into x vector Lm plus Am as function of Lm into n cap cross x vector Lm, and E vector tends to z naught H vector cross n cap, which implies that dp by d omega equals to mu naught c divided by 2k square into mod of summation Lm of minus iota raised to power L plus 1 into Ae as function of Lm into x vector Lm cross n cap plus Am as function of Lm into x vector Lm whole square. It follows from this expression that the electric and magnetic monopoles of a given order L, M have the same angular distribution. The polarization state of the magnetic and electric multipoles of a given order L, M are at right angle to each other. The order of radiation can be determined by measuring the angular distribution. The magnetic and electric nature of the multipole radiation needs measurement of the polarization as well. For a pure multipole of order Lm, we have dp as function of Lm divided by d omega is equals to mu naught c divided by 2k square into mod of Ae as function of Lm into x vector Lm cross n cap plus Am as function of Lm into x vector Lm whole square, which implies that dp as function of Lm divided by d omega is equals to mu naught c divided by 2k square into mod of a Lm whole square into x vector Lm whole square. Mod of a as function of Lm whole square is equals to mod of Ae as function of Lm whole square plus mod of Am as function of Lm whole square, which implies that dp as function of Lm by d omega is equals to mu naught c divided by 2k square into mod of a as function of Lm square divided by L into L plus 1 into bracket 1 divided by 2 into L minus m into L plus m plus 1 into mod of y L m1 whole square plus 1 divided by 2 into L plus m into L minus m plus 1 into mod of y L m minus 1 whole square plus m square into mod of y L m whole square bracket close. So the table lists the value of expressions in the square bracket for L equals to 1 and 2. So for L equals to 1, there exists dipole, and for m is equals to 0, we have 3 by 8 pi sine square theta. Similarly, for L equals to 1, m equals to plus or minus 1, we have 3 by 16 pi into 1 plus cos square theta. and there no value exists for L equals to 1, M equals to plus minus 2. Now similarly for L equals to 2, quadrupole exists, and for M equals to 0 we have 15 divided by 8 pi sine square theta cos square theta, and L equals to 2, M equals to plus minus 1 we have 5 by 16 pi into 1 minus 3 cos square theta plus 4 cos raised to power 4 theta, and for L equals to 2 and M equals to plus minus 2 we have 5 by 16 pi into 1 minus cos raised to power 4 theta. The dipole distribution corresponds to a oscillating dipole parallel to the z-axis for m equals to 0 and along the x or y-axis for m equals to 1 or minus 1. Summation m equals to minus L to I of mod of YLM as function of theta phi whole square equals to 2L plus 1 divided by 4 pi, which implies that summation m equals to minus L to I of mod of x vector Lm as function of theta phi whole square equals to 2L plus 1 divided by 4 pi. If coefficients a as function of Lm are independent of m, the angular distribution is isotropic. This is usually the case with atomic and nuclear radiative transitions. Total power radiated by a pure multipole of order Lm, we have P as function of Lm equals to mu naught C divided by 2k square into mod of A as function of Lm whole square. This implies that P is equals to mu naught C divided by 2k square into summation Lm into bracket mod of AELM square plus mod of AMLM square bracket close. So students, now let us summarize what we have learnt in this module. In this module, we have continued with our study of the multipole radiations. Our next task was to study the various properties of the multipole radiations. We obtained the expressions for the energy density and energy flow in both electric and magnetic multipole radiation. Next, we studied the angular momentum in multipole radiation. We worked out in detail the case of electric multipoles, and magnetic multipole case can be dealt with in a similar fashion. We also obtained expressions for the ratio of angular momentum to energy of the field and commented on the difference between the classical and quantum mechanical expressions for this. Finally, we looked at the detailed angular distribution of the electric and magnetic multipole radiation. We make several comments on the similarities and differences between the angular distribution of electric and magnetic multipoles. We tabulated the angular distribution for the two important cases of dipoles and quadrupole radiation. Thank you.